Welcome back to the Neural Intel Pod. It seems like every day in AI, there's something new and incredible happening.
Yeah, it's really moving fast.
And today we're looking at something that really emphasizes that need for speed.
The need for speed.
That is segment anything model.
SAM2.
SAM2, yeah.
It's pretty cool what they're doing with this.
And what's especially interesting is how PyTorch developers are pushing the limits of its performance.
Making it faster and more efficient, yeah.
Faster, yeah. And we're talking up to 13 times faster, which is
mind-blowing, yeah.
when you think about the real-world implications of that kind of speed.
For sure.
Okay, so before we get into how they achieve that, let's back up for a second. For those who may not be familiar, can you give us a quick rundown of what SAM2 actually does?
Sure. So SAM2 is an AI that can segment images, so it can identify and outline different objects within a picture. So think about, like, you upload a photo of a busy street scene, and SAM2 can pinpoint and outline each individual car, pedestrian, traffic sign, like that.
It's like that magic wand selection tool.
Exactly, yeah. It's like a super-powered version of that.
That's really cool. So it's taking image recognition to a whole new level of detail.
Totally.
And the article we're diving into today focuses on 3 specific ways that SAM2 can be used.
Okay.
Single prompt segmentation, multi-prompt segmentation, and automatic mask generation.
Yep.
Can you break those down for us a little bit?
Yeah, so these are essentially representing different ways of interacting with SAM2 and instructing it on what to segment.
Okay.
Single prompt is like giving it one command: find all the cats in this image.
Okay.
Multi-prompt is like giving it a list of instructions at once. Find the cats, dogs, and birds, for instance.
Right.
And then automatic mask generation is where things get really interesting. It's like telling SAM2 to just go ahead and figure out all the important objects in this image on its own.
Oh, wow. That's impressive. But I imagine all that processing power takes time, especially with really complex images. So how did the developers manage to achieve these incredible speed boosts?
Well, they approached the optimization challenge from 2 angles, which they call fast optimizations and furious optimizations. And fast optimizations focused on streamlining the existing SAM2 code without sacrificing any of its accuracy.
Oh, okay. So like fine-tuning a race car engine. You're not changing the fundamental design, but you're making it run more smoothly.
That's a great analogy. Yeah, exactly.
I like that. Okay. What about the furious optimizations?
So furious optimizations are where they get a little bit more, well, furious. They're willing to trade off a tiny bit of accuracy for a massive boost in speed.
Interesting. So it's a trade-off between precision and speed.
Exactly, yeah.
Now, I'm guessing that's where some of those truly mind-boggling speed gains come from.
You got it.
Let's start with those fast optimizations. Where did they even begin?
They started with what they call eager mode optimizations.
Okay.
And this involves using profiling tools to carefully analyze the code and identify any bottlenecks.
So they're identifying the parts of the code that are slowing things down.
And
then figuring out ways to make them run more smoothly.
Yeah. So they can, see where the program is losing speed and then smooth out those rough patches. One of the most surprising things they discovered was that a lot of the initial speed up actually came from optimizing the data structures that SAM2 uses and how it compresses those masks that it generates.
Interesting. So those low-level details really make a difference.
Yeah. Huge impact on overall performance, yeah.
That's fascinating. It really highlights how optimization can come from these unexpected places.
Right.
But what kind of data structures are we talking about here? What was so inefficient about the initial ones?
Well, it had to do with how the model was storing and accessing information about the segments it was creating.
Okay.
Imagine you have a library full of books, but the organization system is chaotic.
Right.
It takes forever to find the book you're looking for.
Yeah.
But if you streamline that cataloging system, you can dramatically reduce the time it takes to access that information.
Okay, so it's about making the information retrieval process more efficient.
Exactly. Get it. So by optimizing how the information is stored and retrieved, they were able to shave off a significant chunk of processing time.
Right.
What other clever tricks did they have up their sleeve?
So another clever technique they used is called batching prompts. Instead of processing one instruction at a time, they figured out how to group multiple instructions together and feed them to the GPU all at once.
So they're leveraging the GPU's parallel processing power.
Exactly. GPUs are incredibly powerful at handling multiple tasks simultaneously.
Ah, that makes sense. So instead of having one worker doing one task at a time, you're essentially creating a team of workers who can all work together.
Yep.
get things done much faster.
Much faster.
But doesn't that require a lot of upfront coordination to make sure that all the workers are on the same page?
Yeah, that's where the cleverness of their approach comes in. They had to develop algorithms that could efficiently group these prompts together in a way that maximized GPU utilization without sacrificing accuracy.
So it's like a perfectly choreographed
It
dance.
is. For a team of robots.
Totally. Each robot has its own role and they all move in sync.
I love that analogy.
Hmm.
Okay, so they're not just throwing more processing power at the problem, they're finding ways to use that power more intelligently.
Exactly.
But I'm guessing that's just the tip of the iceberg when it comes to these fast optimizations.
Yeah. There's more. They also took advantage of a technique called full graph compilation. Imagine you have a complex set of instructions, but they're written in a language that the computer doesn't understand directly.
Okay.
Full graph compilation is like translating those instructions into a language that the computer can execute much faster.
So it's like pre-compiling a program before running it. You invest a little time up front to make it run much faster later on.
Exactly. Yeah, that's a great way to think about it.
Makes sense. But doesn't that mean the first time you run the program, it's going to be slower because of that compilation time?
You're absolutely right. There is a trade-off there. The initial run will be slower, but subsequent runs will be incredibly fast, especially if you use what's called a warm cache. Imagine you're baking a cake the first time you make it. You have to gather all the ingredients and bake it from scratch. But once it's baked, you can just grab a slice from the fridge whenever you want without having to go through that whole process again.
I see. So you're trading off a little upfront time for a much faster experience later on.
Exactly.
And that makes sense in a lot of scenarios, especially if you're going to be running the same task repeatedly.
Right.
But let's shift gears a bit.
Okay.
We've been talking about those fast optimizations, which focus on making the existing code run more efficiently.
Right.
But you mentioned earlier that they also have these furious optimizations, where they're willing to sacrifice a bit of accuracy for even more speed.
Right. Yeah.
Tell me more about that. What kind of compromises are we talking about?
Okay, so one of the most significant furious optimizations involves switching from what's called float 32 to float 16 calculations.
Oh,
And to understand this, you need to know that computers represent numbers using bits, zeros, and ones. Float 32 uses 32 bits to represent a number, while float 16 uses only 16 bits.
so it's like using a lower resolution image. You're sacrificing some detail to reduce the file size. But how does that translate to faster processing?
It's not just about the file size, it's about how GPUs are designed. GPUs are incredibly efficient at handling lower precision calculations, like float 16.
So it's like you're giving the GPU a language it understands much better.
Exactly. By speaking its language, you can get it to work much faster.
That's really interesting. But how much accuracy are we actually sacrificing here? Is it noticeable?
That's the key question, and in most cases, it's barely noticeable.
Hmm.
Remember, we're talking about reducing the number of bits used to represent a number. It's like rounding a number to the nearest tenth instead of the nearest hundredth.
Okay, so the overall result is very similar, but the calculations are much faster.
Exactly.
That's a great way to put it. It sounds like a pretty clever compromise, especially when you consider how much faster things become.
For sure. And they didn't stop there.
Oh.
They found that even simple things like moving more of the image preprocessing tasks to the GPU yielded noticeable gains.
Wait, they weren't already doing all the image preprocessing on the GPU?
You would think that would be the obvious place to do it, but sometimes these optimizations are hidden in plain sight.
So it's like they were constantly looking for ways to streamline the entire process from that initial image preprocessing all the way to the final segmentation output.
Exactly, yeah. They really left no stone unturned.
This has been really insightful. I'm already starting to see how these optimizations could translate into real-world benefits, making AI applications faster, more responsive.
Yeah.
But we've only scratched the surface of their work.
We have, yeah. There's more to come.
When we come back, we'll dive into some even more advanced techniques, including something called ahead-of-time compilation, and how they put all these optimizations to the test in a real-world cloud deployment. Don't go anywhere.
We'll be right back. You know, one of the really fascinating parts of this is how they tackled the challenge of deployment.
Okay.
You know, it's one thing to make an AI model run faster in a lab setting,
Right.
but it's quite another to get it working seamlessly in like a real-world cloud environment.
Yeah, it's like a concept car versus a car that can actually handle like daily driving.
Exactly. And that's where this thing called AO inductor comes in, or AOTI.
AOTI.
Yeah.
Okay. How did that help with deployment?
So think of it like pre-baking a cake
Okay.
instead of baking it from scratch every time someone wants a slice.
Right.
So with AOTI, you're compiling that AI model into a very efficient, ready-to-run format,
Yeah.
which is incredibly useful for cloud deployments where servers need to be able to spin up and down really quickly.
So it's all about minimizing those startup times.
Exactly.
Making the AI ready to go at a moment's notice.
Yeah.
That makes sense, especially in that cloud environment where speed and efficiency are so important.
Exactly. But there is a challenge here
Well,
when dealing with dynamic prompts,
yeah.
meaning those instructions given to the AI can vary from task to task.
Hmm.
So pre-compiling works great
Right.
when you know exactly what the AI is going to be doing.
Right.
But what if the instructions change?
Yeah. So it's like having a pre-baked cake that can magically transform into different flavors
Yeah,
and shapes depending on what the customer orders.
exactly. Yeah.
That's a tough problem.
It is a tough problem to solve.
Yeah.
But the developers are working on ways to overcome this by exploring techniques that allow for some flexibility
Right.
within that precompiled model.
I see.
So it can adapt to different prompts without having to be recompiled every single time.
So they're trying to find that sweet spot
Yeah.
between that pre-compilation efficiency and that runtime flexibility.
Exactly.
So let's assume they crack this problem.
Okay.
What kind of impact could this have on AI deployments?
Well, I mean, it could be huge. Imagine, being able to deploy AI models in the cloud that can handle all sorts of tasks, adapt to new instructions instantly, but still maintain that incredible speed.
Hmm.
I mean, this would open up a whole new world of possibilities,
Mm.
especially in things like real-time decision-making, personalized recommendations, and interactive experiences.
That is an exciting vision. Sounds like we're really on the cusp of a major breakthrough in AI deployment efficiency.
For sure.
But even after all of these optimizations, did they manage to squeeze out even more performance? Were there any other tricks they had up their sleeves?
Well, believe it or not,
Yeah.
even after implementing all those optimizations, they were still able to find more ways to improve things.
Really?
Yeah, they found that by moving even more of those image preprocessing tasks over to the GPU,
Wait, so they weren't already doing all of the image preprocessing on the GPU?
you would think so, right?
Yeah.
Yeah.
But sometimes these optimization opportunities are hidden in plain sight.
So it takes,
A keen eye,
yeah,
a willingness to experiment, to really uncover those hidden gems.
that's a great lesson for anyone really working in software development or any field for that matter.
Yeah,
Never assume you found all the optimizations. There's always room for improvement.
absolutely. And in this case, that extra effort paid off.
Mm-hmm.
By moving more of that image preprocessing workload to the GPU, they were able to reduce the strain on the CPU,
Mm-hmm.
free up more resources, and that further improves the performance.
So they were basically fine-tuning the entire system
Yeah.
from that initial image all the way to that final segmentation output.
They were making sure that every single part of that system was running as efficiently as possible. That's impressive, the attention to detail that they put into this optimization.
For sure.
It really highlights a holistic approach to optimization.
Yeah.
You can't just focus on one area and expect to get these great results. You really need to look at the entire system.
Yeah. Look for opportunities to improve efficiency at every stage.
So they've got these optimizations,
Yeah.
the fast and the furious,
Right.
but did it actually work in the real world?
Right. Well, that's the big question. And
Yeah.
the answer is yes.
Okay.
They actually put these optimizations to the test in a real-world cloud deployment
Oh, wow.
using this platform called Modal,
Okay.
which allows developers to build and deploy these serverless applications.
So they actually went the extra mile
Yeah,
to see how these optimizations performed in a real-world setting, huh?
they did. And the results were impressive. Significant reductions in processing times, improved responsiveness. Even those queue times, remember?
Yeah, the wait time.
Yeah, the wait time for tasks was reduced simply because the AI was now working so much faster.
So it's a ripple effect of efficiency.
It is throughout that entire system.
I like that. That's
Yeah.
really cool. And that's optimization done right. It's not about just making one component faster.
Yeah,
It's about improving the performance of that entire system,
the whole thing.
creating that smoother, more efficient workflow.
Exactly.
This has been incredible so far, uncovering all of these clever optimizations,
It's been fun.
seeing how they all come together to make these amazing speed gains.
Yeah.
But we're not quite done yet. When we come back, we'll wrap up this whole deep dive
Okay.
by really exploring the implications of these advancements
Right.
and what they mean for the future of AI. Stay tuned. It's amazing how far AI has come in such a short amount of time.
It really is.
We started talking about AI evolving at warp speed, and these optimizations to SAM2 are a great example of that.
Yeah, the progress is remarkable.
Or we're just scratching the surface, right?
Oh, absolutely, yeah.
And you remember those incredible speed improvements?
Yeah.
Up to 13 times faster.
It's mind-boggling.
It really is. It's mind-boggling to think they actually achieved those gains in real-world tests.
Those numbers weren't just theoretical. It was the result of, that meticulous optimization, really clever engineering, and a deep understanding of the hardware and the software.
Yeah, so this isn't just some pie-in-the-sky future tech. This is happening now, and it's going to have a huge impact on how we use AI in all sorts of applications.
Absolutely. Think about all the areas where speed and responsiveness are critical,
Yeah,
like self-driving cars, medical diagnosis, real-time language translation, personalized recommendations.
right.
It could revolutionize those
It's
fields.
like we're removing those speed limits from AI,
Yeah.
allowing it to operate at a level we've never seen before.
Yeah.
Imagine AI that can process information, make decisions, and interact with the world in real time,
Yeah.
seamlessly and effortlessly.
It's like AI-powered experiences would become instantaneous, intuitive, and truly integrated into our lives.
Wow. No more lag, no more waiting, just a seamless flow of information and action. It's an exciting vision. But it also raises some interesting questions. If we can make AI this much faster, what other bottlenecks are out there?
Right. What other things can we break? What new applications will become possible?
Right. It's really incredible.
And the best part is we're only just starting to explore the answers.
Hmm.
This article mentioned a repository called torch, where developers are pushing these boundaries even further.
So there's a whole community of people out there who are dedicated to making AI faster, more efficient, and more powerful.
It's inspiring.
Yeah, it really is. And it reminds me that we're living in a time of just incredible technological advancement. Who knows what's next?
It's true. The future of AI is full of possibilities.
And thanks to all these researchers and engineers, those possibilities are becoming reality much faster than we ever imagined.
They really are.
So for anyone listening, we hope this deep dive has sparked your curiosity and it inspired you to explore this world a little bit more.
It's a fascinating world.
It really is. Until next time, keep learning, keep exploring, and keep that neural curiosity burning bright.